Hi everyone, today we'll be discussing inductors and we'll go over the properties that they will have. So the main characteristic here is that similar to capacitors, inductors are also used for storing energy in electrical circuits. They are again passive elements and they can be used in a variety of applications that we'll look into very soon. So as you can see here, we have inductors that are in different shapes, but generally speaking, what forms an inductor is a twisted layer of wire that is obviously housed around um, some element that has some preambility. Now, they do have various applications in power supplies, transformers, radios, TVs, radar, and electric motors, and so inductors play a key role in all of these basically element. Generally speaking, any wire has an inductance. However, when you coil up the wire, you obviously get significantly higher inductance. And you might know this because if you have ever built non-permanent magnets, then you know that if you coil up more wires, you get a stronger magnet, which directly is correlated with the inductance of the element you're using. What's important though is the mathematical expressions that correspond or relate the voltage and the current within an inductor. So the voltage in an inductor is given by L di dt, L being the inductance of the inductor. It's measured in Henry, which is volt second per ampere in terms of unit. Generally speaking, the voltage that is developed in an inductor tries to oppose the changes in the current. So we know this from the rules that we have learned in physics, that basically the voltage that is generated by an inductor tries to oppose the current that is changing. So if the changes of the current are very large, then you get the largest voltage. The inductance is directly related to the shapes that are being used. So we will only look at one scenario, but obviously when you take a course in electromagnetics, you may consider a variety of options. But if we are looking only at the scenario of a cylinder, then overall the inductance is given by the number of turns squared. So as you can notice, the number of turns play a key role in increasing the inductance. The area, the surface area, and we're talking about this cross-sectional area, and then L being the length. So the longer the length, the lower the inductance. There's also a factor called mu that is related to the preambility of the core material, and obviously that changes for different materials. The current is given by the integral of both sides of this expression. So if we go back here and take the integral, it will be Vt dt over T naught 1 over L plus the initial current, and that will give you the overall current. The power is obviously again given by Vi, which is L di dt times I. Now if you want to find the total stored energy, you have to take the integral of both sides with respect to t, and that is when you arrive at half Li squared. So if the current through an inductor is constant, then the voltage is zero. So basically what happens is, when you're looking at DC conditions, an inductor acts as a short circuit. So it's exactly the opposite of a capacitor. In DC conditions, a capacitor charges and acts as an open circuit. In DC conditions, an inductor acts exactly like a closed circuit. It basically acts like a wire. So generally speaking, inductors do not want the current through them to change quickly, and we can use this to try to generate very large voltages. And for example, that is used in a starter motor in your car. There is an inductor that is placed there that is used to generate the necessary voltage to get the electric motor to go. And that usually is one of the things that breaks, and then you will try to fix it when your starter motor actually fails. But excuse me, the general idea here is that you cannot change the current inside an inductor quickly. If you do try, it will generate a very large voltage, and that voltage can be used for obviously other purposes. Obviously, inductors are not ideal. Obviously, in non-ideal scenarios, they dissipate energy, they dissipate, and they have resistances, and many other parameters, right? So, and also capacitance. So, a non-ideal inductor has capacitance, has resistance, and dissipates energy. But we are going to consider ideal scenarios where the energy is not dissipated, there is no capacitance, and the resistance is equal to 0. You may ask, where is the stored energy for an inductor? The stored energy is in the electromagnetic that is built around the inductor. That's where the stored energy is. And when you try to change the current inside the inductor very quickly, you're going against that electromagnetic stored energy or magnetic energy that is stored there. And that magnetic energy will actually oppose the changes that you're trying to apply. So let's look at the series and parallel scenario. Inductors, unlike capacitors, act exactly like resistors. So when you put them in series, you can write down the expression for them. Again, V is equal to V1 plus V2 plus V3 all the way to Vn. If you actually write the general expression, what you arrive at is that the equivalent inductance is given by the sum of all the inductances. So the same behavior, and if we do the same thing for parallel inductors, we notice the same thing again, that if we use the currents, we arrive at this expression, and what we determine is that the equivalent inductance is given by the same expression we were using to find the equivalent resistance. So capacitors are the opposite of resistors, and inductors are the same as resistors when we're looking at equivalent resistances. This is a summary table that maybe would be helpful to put on your cheat sheet if you're trying to bring one to the exam. It tells you what the equivalent resistances are, equivalent capacitances are, and equivalent inductances are. It has all the expressions for the currents and voltages, and it also has all the expressions for parallel and series scenarios. So inductors don't have as many applications as capacitors. Generally speaking, in circuits we try to use capacitors because inductors are very bulky, and that's always a shortcoming. They're very difficult to design in surface mount components, so overall they're avoided. What they are used for is they're used to design filters. So unlike a capacitor that is an open circuit for DC, inductors are a short circuit for DC, but then they're an open circuit for high frequencies. So you can use them to design low-pass filters in conjunction with a resistor, or you can use them in conjunction with a capacitor and a resistor to design a band-pass filter. And that's what is used inside, for example, your radio to eliminate, for example, the radio stations that you don't want to listen to, and only listen to the radio station that you're interested in. From here on, we'll solve some problems, and thank you very much.